For the spin field effect transistor, we've developed an efficient approach for using the transfer matrix formalism for spin transport. We've modeled the spin injection and detection properties of the ferromagnetic electrodes on semiconductors, and we've been able to use these to do the first self-consistent simulation of a spin FET in the drift diffusion regime. And finally, in the case of magnetic tunnel junctions, we've implemented an extended Huckel theory simulator which can be used for atomistic simulations. This is a very general purpose simulator and it can be used in many other situations also. But by applying it to the magnetic tunnel junctions, we've identified Fermi level spinning as a very critical effect in MTJs. And we've also implemented an efficient approach for using alloy electrodes. So with that, I come to the acknowledgements. And it's really impossible to acknowledge all the people who made such important contributions to my time at Stanford. And maybe a lot more of it will be in my thesis, but I'll make a quick attempt here. I must start with Professor Krishna Saraswat, who's been an excellent advisor, and I really could not have asked for anyone better. I can go on, but again, I think I'll just move on here. I'd like to thank Professor Nishi, Professor Shan Wang, and many of the other faculty at Stanford who contributed to my work here and helped me with my projects. I'd like to thank Intel Corporation for funding a lot of this work and also for the Intel Fellowship that's been funding me for the last year. And in Intel Corporation, I'd especially like to thank Dr. Dmitry Nikonov for helping me through a lot of this work and being a great technical contributor and also a great person to talk to about problems and also outside of it. And through my internships at Intel, I've got to interact with some really smart people, Young, Sasikant, and Pranav, and I'm really thankful for that. Some of the members of the Saraswat group I have interacted with a lot more than the others, and especially I must mention Jason Lin, Donghoon Lee from Professor Shan Wang's group, and Donghook Nam. And it was a lot of fun working with them in the lab, outside the lab, and I hope I can keep in touch with them later and have made really good friends over here. I'd like to thank the rest of the Saraswat group also for all the discussions and all the great times we've had together. SNF staff and lab members, of course, everyone knows they play such an important role in all the work we do there, and I can't end without thanking them. And finally, I must thank all my friends and family, who, of course, outside all this research work, made this entire experience at Stanford really wonderful. And with that, I'd like to end it. Thank you very much for joining me.
So the talk is now open for questions.
Yeah, I've been familiar with the spin tunneling. So it's the same mechanism as electron tunneling through the barriers?
It's the same mechanism, except so if you assume you have an amorphous material through which you're tunneling, often you can describe this with a much simpler model. Whereas in the case of magnesium oxide, because by annealing these devices you can have a nearly crystalline structure, it's more important to now account for the actual electronic structures in both the electrodes and the magnesium oxide. But the physics remains the same. It's still Schrodinger equation solution in the device. The band structures become more.
Why does the presence of an insulator make the spin polarization? Like when you inject it to a semiconductor, why does it become polarized? Is there a physical reason for that?
Yeah, there is. So the reason for this lack of spin injection from ferromagnet into semiconductors is called conductivity mismatch, because you have this large conductivity mismatch between semiconductor and ferromagnet. So you can imagine that to support a certain amount of spin polarization in the current, you need a certain electrochemical splitting in the ferromagnet, whereas to support the same amount, you would need a much larger electrochemical splitting within the semiconductor. And in order to have this different electrochemical splitting in the two materials, you can't put them in contact together, but you need to have some kind of a tunneling resistance or spin selective resistance. That's the intuition you can get on that. But there are other reasons to have that insulator layer over there, because even experimentally when you make this device, if you put a ferromagnet directly on a semiconductor, you have diffusion at the interfaces, and these ferromagnetic atoms which are not part of your electrode have randomly oriented spins, and they can spin scatter your electrons and lead to spin relaxation. There are a couple of important reasons to have it.
if you scale down in the spin path?
Yeah, there are, in the ideal spin FET, you would really have a device where your semiconductor channel could be just tens of nanometers and you would really not be in a drift diffusion regime. But the case that we studied is also the case which is being more experimentally studied at the same time nowadays, because when people are making spin FETs nowadays, they're first doing it on long channel devices. And of course, similar short channel effects apply to the spin FET also, because the electron transport is almost by the same mechanisms. The only additional effect actually comes from these two contacts, where the contact resistance essentially changes as a function of this parallel anti-parallel configuration. But you're right, short channel effects also affect this device. The nice thing is that, or the hope is that in such a device, the short channel effect might give you a large off-state current, but because you also have this control on the relative magnetization of your electrodes, you can switch it into anti-parallel and cut down your off-state leakage currents.
Well,
This is Dimitri. I have a question,
Yes, indeed.
which might be a difficult one. So that the mainstream of the spin common junction is to have the coupled ion avoid as the ferromagnet. But you have made this extended field theory simulation, and it can help you in search of other materials
Yes.
as ferromagnet.
Yes.
Have you tried other materials, and if not, where would you look? What sort of materials would you look for better ferromagnets?
For better ferromagnets or better insulator materials?
I'm interested in ferromagnets, but if you have something to say about the insulator material, that we can go ahead.
Okay. So among the ferromagnets, we know that we have access to these three useful ferromagnetic materials, nickel, iron, and cobalt, and we can use them in alloys in these devices to improve the spin selective properties. But I think this problem is complicated by the fact that not only the electronic structure plays an important role, but also the effects of Fermi level pinning and how crystalline the entire device remains after annealing can play an important, very important role. So while we can study the effect of the electronic structure by using other alloy configurations like nickel iron, cobalt iron, if we want to actually make a very good estimate of what the total MR ratio in such a device would be, it is much better. I believe it is better done in an experimental fashion where you first identify effects which can affect MR ratio, for example, Fermi pinning. And then if we can see that by introduction of boron and cobalt and boron, we can change the interface or change the Fermi level pinning, we can get higher MR ratios from such a device. And similarly, for the case of other insulator materials, I haven't looked into it, but we can use this similar approach to look into that also. And if I had to start, I would look for materials again which crystallize with a similar lattice constant to iron and see if they have good spin selective properties.
Dimitri, just this is Krishna. Just so that you know, this was just the seminar part of it. This will follow by roughly an hour examination by the committee. So we'll break for another 5 minutes following this public part, and then 4 of us, you and 3 of us here, will have a chance to ask many more questions. So I hope you are staying for another hour.
Oh, yes, of course.
Yes,
I have one question following up on that. So I'm just wondering how you can comment on the accuracy of the extended control model. Because imagine that the geometry of the interface between the iron and the lithium oxide will obviously be affected.
Yeah.
The spatial positions that you have
Yes.
will be a strong function of the parameters.
Yeah, right. Yeah. So what you can do is, and the way we input these particular spatial configurations is from experimental studies when people can actually do EM cross sections and look at that.